This video concerns advanced users. It focuses on the implementation of hypothetical decision policies for developing an automated risk management agent that assesses, in real time, the security compliance of a third-party controlled infrastructure as a service resource, against a defined set of security rules. The risks considered span various areas, such as availability, integrity, and confidentiality, involving computing resources such as virtual machines. These risks may impact storage resources and involve several sensors, which are small and simple software components designed to monitor specific aspects of cloud computing resources related to one or more security domains. Examples of sensors include disk-free space, tracking storage availability, CPU usage, monitoring processor load, network traffic, tracking bandwidth usage. In this video, we implemented the following hypothetical decision policies to determine whether the agent should ignore, or not, a reported risk. If the risk value exceeds 0.9, the risk is not ignored. If the risk value is below 0.9, generally the risk is ignored unless specific conditions apply. These are called context-dependent decisions. So if the risk involves the sensor's CPU usage or network traffic and does not concern the integrity risk area, the risk is not ignored. Similarly, if the risk involves the sensor's CPU usage or network traffic and pertains to virtual machine number 4, the risk is also not ignored. The data provided in this example of application through the run screen are typically provided from databases or APIs in real-world applications. We are now set to begin implementing the automated risk management agent. To proceed, we will access the dashboard to create the options Ignore the Risk and Not Ignore the Risk, along with supporting scenarios involving sensors, risk areas, and virtual machines. We will start by creating the two options. The first option is Ignore Risk. We can also create its negation using the toggle button. Next, we create the first scenario. The risk value is less than 0.9, and we associate it with both options. Then, we create the second scenario. The risk value is greater or equal 0.9, and we associate it with the Not Ignore Risk option. Clicking on Conflict Resolution, we see that RAISON has detected a conflict in the scenario where the risk value is less than 0.9. We select Primary Choice and set Ignore Risk as the default preference for this situation. Now, we define the two specific situations, or contexts, where the risk should not be ignored, even if its value is less than 0.9. The first situation applies when the risk involves sensor CPU usage or network traffic, and the risk area is not integrity. There is no further data to alter this decision, so we select No. Now, since we have a second situation to implement, we select Yes and we proceed to the second situation, where the risk is related to the sensor's CPU usage or network traffic, and it pertains to virtual machine number 4. There is no additional data to change this decision, so we select No. Since there are no other specific situations to implement, we select No once more. We click on the decision policy to view the created policies, then click on Initial Scenarios and Options to customize the knowledge representation using Prolog, and we use the toggle button for this. We start by incorporating 4 variables, risk, sensor, area, and VM, for virtual machines, into the names of the 2 options. These variables will later be used in predicates to represent these key features of our problem. Now, we navigate to Manage Elements to customize the automated representation of the scenario elements proposed by RAISON. We start with the element related to sensors and virtual machines by unchecking input data since it is not input data. We then remove RAISON automated representation, define custom predicates to represent sensors and virtual machines, and finally define the constraints described in natural language. We can see the different sub-elements that RAISON automatically creates each time we enter text separated by commas. Once we finish, we navigate to the first element to enter the message that the user will see when providing a value. In our illustration, this is user-provided input data, whereas, in a real-world scenario, this information would typically be retrieved from a database. Then, we move to the second sub-element and uncheck it, as it is not input data, and we type in a natural language representation of the Prolog encoding. Next, we move on to the third sub-element, which is also user-entered data in our illustration, although this shouldn't be the case in a real application, and we type the message that the user will see when he provides a value. Finally, we move on to the last sub-element, uncheck it because it is not input data, and type in a natural language representation. Now let's move on to the element involving sensors and the risk area. Let's uncheck the data entry box, remove the automated representation, and proceed with the custom Prolog encoding. Although it's not explicitly shown in the video, we can reuse the previous encoding with just the necessary modifications. RAISON safeguards the 2 common sub-elements and permits edits only to the sub-element related to the virtual machine, as we are now dealing with a risk area that requires us to define a custom predicate and the corresponding constraint. So we jump straight to the third sub-element, which is also user-entered data in our illustration, although this shouldn't be the case in a real application, and we type the message that the user will see when he provides a value. Finally, we move on to the last sub-element, uncheck it because it is not input data, and type in a natural language representation. Now let's move on to the automated representation of the first scenario. We uncheck this option since it is not input data, delete the default representation, and customize it by defining a predicate for risk along with the corresponding constraint. Next, we move on to the first sub-element, which is also user-entered data in our illustration, although this shouldn't be the case in a real application, and we type the message that the user will see when he provides a value. Finally, we move on to the last sub-element, uncheck it because it is not input data, and type in a natural language representation. Now let's move on to the last element to customize the automated representation of the second scenario. We uncheck this option because it's not input data, we delete the default representation and customize it using the previous encoding, making only the necessary change to the corresponding constraint, namely that the risk value is greater than or equal to 0.9. Next, we move directly to the second sub-element, as the first one is protected by RAISON due to its use in the previous encoding. We uncheck it because it's not an input data and proceed to enter the natural language representation. We switch to natural language and we see the natural language representation of all the elements. We can now go to the menu and click on the Run button. The necessary code is instantly generated and deployed on RAISON. We are ready to test the system we have developed. More precisely, we observe that when the risk value is below 0.9, the agent ignores the risk, whereas if it is higher, it does not. Now, we observe that when the risk value is below 0.9, the sensor is CPU usage, and the risk area is integrity, the agent correctly decides to ignore the risk. However, if the risk area concerns availability, the agent does not ignore the risk, as this is a specific case where the risk must be considered even if its value is below 0.9. The same applies when the number of virtual machines is 4, as this is the second specific case where the risk should not be ignored, despite the risk value being below 0.9. However, if the number of virtual machines is not 4, the agent correctly decides to ignore the risk. This concludes this video. Thank you for watching.